So first I want to talk a little bit about conic sections and why they're called that. So a cone in mathematics is what we would think of as a double cone, where a cone and an upside down cone and they meet at a point. So if we slice through the cone with a plane in different ways, we get different shapes as the cross section, and these are called conic sections. They're sections of the cone. So notice that if we put the plane perpendicular to the axis of the cone, that we get a circle as the cross section, and we can tip this shape down and look in there and see, sure enough, it's a circle when we cut through the cone in that way. And then if we cut through the cone at an angle, we get an ellipse. So if you tilt and look inside, you see that you get an ellipse. Then if you slice with the plane and it's parallel to one of the sides of the cone, then the shape you get is a parabola when you cut through the cone. These parabolas, some of them are functions, but some of them are not going to be functions. So we're leaving the world of functions and entering the world of analytic geometry. We still have equations that describe shapes and make really interesting graphs, but they are not functions. So we also can get a parabola if we cut with the plane parallel to the other side of the cone. And then the third conic section. So the basic three are ellipse, parabola, and hyperbola. If you slice through the cone parallel to the axis of the cone, then you get a hyperbola that has two arms or two pieces to it. Then there are three degenerate conics, they're called, where they're unusual cases. So if you slice right at the point where the two pieces of the cone meet, you get a single point only. So that's called a degenerate conic. And then if you slice with the plane parallel to the side of the cone on both halves, then you get a single line rather than the parabola. And if you slice vertically, but right at the point where the two halves of the cone meet, then you get a pair of intersecting lines rather than the hyperbola. So those are called degenerate conics. So the first ones we're going to study are parabolas. And we're going to start with the vertex at the origin, and then we're going to allow the vertex to be anywhere. And you'll see that the shifting works a little bit differently than it does with functions. And then we're going to look at an applied problem. Everybody will have applied problems. Each person's will be a little bit different. So the geometric definition of a parabola is it's the collection of all points P in the plane that are the same distance little d from some fixed point capital F as they are from a fixed line, capital D, and the point F is called the focus of the parabola, and the line D is its directrix. So as a result, the parabola is the set of all points for which the distance from F to a point on the parabola is the same as from D to a point on the parabola. So this would be your point on the parabola. And let's look at another one of these interactive figures. Where we can see this illustrated. So this is a parabola. And as I move the point P, difference it makes to have the focus pushed way down inside the parabola, it makes the parabola a lot narrower. And then if the focus is way far away from the vertex, it makes a much wider parabola. So now let's look at what happens if we move the point where we are on the parabola and see how those two red sticks stay exactly the same length as each other, no matter where I am on the parabola. So this is the geometric definition of a parabola. From focus to point on the parabola, that length is equal to point on the parabola to the directrix line. So that's going to be true for every parabola. So we start by looking at the familiar ones, y equals x squared, but then we are also going to look at parabolas that open sideways. So actually this lesson starts with looking at the sideways opening ones first. So in geometric land, a parabola can open upward or downward or right or left. Well, you can see that these two would still be functions, but these two clearly not functions. So the equation of a parabola with the vertex at 0, 0, and the focus a distance a away is y squared equals 4ax. And there's a reason for writing it in this form. This quantity 4a is significant, and it's called the focal diameter. It says, how wide is the parabola at the point that's the focus? This distance is the focal diameter. How far across is the parabola if I'm at the focus? So this line segment joining these 2 points is called the latus rectum. You'll hear it said lots of different ways. Formal Latin would be latus rectum, but you rarely hear that. So its length is 4a because this distance is a from the vertex to the focus, and then the focal diameter is 4a, so each side is going to be 2a because of the symmetry. So this is the focal diameter, the quantity 4a that you see in the equation. So here's a little chart if you like charts that organize the information for you. And here's some problems where we're supposed to find the equation of the parabola given some information. And we're supposed to find the equation and the 2 points that define the latus rectum and graph the equation. I always like to put these on a sketch. So I have the vertex at 0, 0, the focus at 0, 2. So that tells me this parabola has to be opening upward because the focus always has to be inside the curved part of the parabola. So I know that this distance from focus to vertex, that distance is a, and in this case that is 2. So we know a is 2. Well, I start from my home base parabola of y equals x squared, and then I'm in geometric land, so it's x squared equals 4ay, but that's the opens upward downward formula. So I'm going to have x squared equals 4a is 8y. So here's my equation of this parabola. And then the 2 points that define the latus rectum, this 8 is the focal diameter. So you stand at the focus and go 4 to the left and 4 to the right, so that the entire way across the focal diameter is 8. And then we just look at our sketch here to see what are the coordinates of these points. And I went to the right 4 and up 2, so 4, 2. Then I went to the left 4 and up 2, so negative 4, 2. And you can abbreviate this LR points, latus rectum points. So here's my equation and my 2 points that define the latus rectum. And we graphed the equation. Okay, the next example, I know where the vertex is. And the directrix is the line x equals negative 1/2. Well, that's a vertical line. And I know the distance from directrix to vertex equals from vertex to focus. So if it's a distance of 1/2 from the vertex to the directrix, then it's a distance of 1/2 from the vertex to the focus. And then I know that A is 1/2 because it is that distance. So then 4A is going to be 2. This parabola is opening to the right. So rather than x squared equals something times y, it's going to be y squared equals something times x. And in this case, it's the 4A, so 2x. So 2 is the focal diameter at the focus. The parabola is 2 wide. So that means I need to go up 1 and down 1 so that my focal diameter is 2, and then I can draw my parabola. So I found the equation. I need the 2 points that define the latus rectum, and I've graphed my equation. So let's read these latus rectum points off my graph. So the latus rectum points are 1/2, 1 and 1/2, -1. So here's my equation and my latus rectum points. Okay, so that's if the vertex is at the origin. Not every parabola has its vertex at the origin. So this little chart shows what changes. Well, everywhere you have x, it goes to x minus h. And this acts in the same way as it did when we were making horizontal shifts to functions. But now the y is going to also act in this way. And so this might remind you of how the circle worked, of you subtracted the h and the k for a circle because that was a geometric figure and not a function. So let's look at this example where we have the vertex is at 1, 2, 3, 4, -2. So here's my vertex. And my focus is at 1, 2, 3, 4, 5, 6, -2. So because of the arrangement of the vertex and the focus, I can tell that this parabola opens right because the focus has to be inside the curved part of the parabola. So the distance from vertex to focus is 2, so A is 2. And then I know 4A is going to be 8. And this is not y and x squared, this is x and y squared. So I need to adjust for my vertex being moved. So I'm going to have y minus the y coordinate of the vertex, which is -2. So that's going to have a plus, equals 4a is 8, and then x minus the x coordinate of the vertex. So this is going to be the equation. And then 4a equals 8. So at the focus, the focal diameter is 8, so up 1, 2, 3, 4, and down 1, 2, 3, 4. And we can draw the graph. And then we can say where the latest rectum points are by looking at the graph. 1, 2, 3, 4, 5, 6, comma, 3, and 6, comma, -5. And there we go. Okay, so let's pause here and I'll come back and do another example and finish off the section.